Big O notation. It's the language we all use to talk about how our code scales. But here's the thing, a lot of developers, even experienced ones, get it subtly wrong, and those little mistakes can lead to some big problems. So let's dive in and get it right. So let's just kick things off with a quick question to get your brain warmed up. Is O of n squared over 2 the same thing as O of n squared? Now, the answer might seem obvious, but the reason why is what trips people up. Don't worry, we're going to get to the bottom of this. And look, getting this right really matters. This isn't just some academic exercise. These misunderstandings pop up in code reviews, in system design meetings, and yeah, they can absolutely sink you in a technical interview. So in this explainer, we're going to fix these common mistakes for good. Okay, so before we can really master what Big O is, we've got to do a little unlearning. We have to be crystal clear on what it isn't. And that starts with tackling one of the biggest misconceptions out there. You've heard this a million times, right? Someone analyzes a pretty simple loop and says, yeah, this algorithm runs in O of n seconds. I mean, it sounds smart, it sounds precise, but it's completely wrong. So here's the deal. The number one thing to remember. Big O is about the growth rate, not actual wall clock time. It's not a stopwatch. It describes how the number of operations scales up as your input size gets bigger. So the right way to say it, the runtime grows linearly with the input. That sounds like a pro. And to really speak this language fluently, we need to go beyond just Big O. We need to get to know its siblings. Using the right notation shows a much deeper level of understanding. Precision is everything here. Think of it like this. Big O is the ceiling. It gives you an upper bound. The algorithm's runtime will grow at most this fast. Big Omega, on the other hand, is the floor. It's at least this fast. But Big Theta, that's the holy grail. It's a tight bound. It means the growth is exactly this fast. When you can, you should always aim for a theta analysis. All right, let's get to the fun part. Busting some of the most common myths about Big O. I promise, getting these right will put you way ahead of the curve. Ah, the classic. You see two nested loops and your brain just screams, O of n squared, right? It's like a reflex. But it's a shortcut that can hide what's really going on under the hood. Now, think about a case where the inner loop actually depends on the outer one. What happens is you don't get a perfect square of work. Instead, you get this triangular workload. The total number of operations ends up being something like n times n minus 1, all divided by 2. And this brings us right back to our first question. In the world of Big O, we drop constant factors, like that divide by 2, because we only care about the dominant term as n gets huge. So O of n squared over 2 simplifies to a tight bound of theta of n squared. The initial hunch was right, but the reason why is so much more important. Okay, on to myth number 2. You analyze a function that takes two different inputs. Let's call them n and m, and you correctly figure out the complexity is O of n plus m. It is so tempting to just clean that up, right? Drop the m and call it a day at O of n. But that is a trap. The rule here is actually pretty simple. You can only drop a variable if you know for a fact that its growth depends on the other one. But if n and m can grow totally independently, think about the number of nodes and edges in a graph, for example, then you absolutely have to keep both. O of n plus m is the precise and correct answer. Oh man, this next one is super sneaky. It trips up so many people. You write this elegant recursive function, you're not making any new arrays or lists inside it, so you confidently say, yep, O of 1 space complexity, constant space. But you've forgotten about a major hidden cost. And that hidden cost? It's the call stack itself. Every single time your function calls itself, a new frame gets pushed onto the stack, and that stack takes up memory. So your space complexity is actually tied to the maximum depth of your recursion. A perfect example is a recursive binary search. It doesn't use O of 1 space, it actually uses theta of log n space. Now let's do a little deep dive on a concept that can feel a bit tricky but is incredibly powerful, amortized analysis. Honestly, understanding this is one of those things that separates good engineers from truly great ones. It explains the real-world performance of data structures we use constantly. To get our heads around this, let's use a simple analogy. Picture yourself adding cups one by one to a serving tray. Putting each individual cup down is super fast, right? It's a constant time operation. No big deal. But then, the tray gets full. You can't add any more cups, so you have to stop what you're doing, go find a much bigger tray, and then move every single one of those cups from the old tray to the new one. That one operation is incredibly slow and expensive. Well, this is exactly what happens with a dynamic array, like a list in Python, when you keep appending elements. So what's the real cost here? Well, even though one of those operations can be painfully slow, those expensive resizes happen so rarely that their high cost is spread out or amortized over all the cheap operations. When you average it out over a whole bunch of appends, the cost for each one is, believe it or not, constant. It's O of 1 amortized. And this is exactly why being precise matters so much. You have to specify what case you're talking about. For that dynamic array, the absolute worst case for a single append is O of n, but the amortized cost is O of 1. You see the same thing with hash tables. The expected time to get an item is O of 1, but the worst case, if everything collides, is O of n. Knowing the difference is critical. Okay, so we have all this knowledge. How do we actually use it when we're under pressure in a coding interview? Well, it all comes down to how you communicate your analysis. Here's a dead simple 4-step framework you can use every time. First, state your assumptions. Second, be explicit about the case you're analyzing. Is it worst, average, or amortized? Third, give your time complexity analysis. And fourth, and please do not forget this one, analyze the space complexity, including that pesky call stack. Following this structure just makes you look methodical and thorough. And this is what a pro-level answer really sounds like. You're not just spitting out a number, you're giving the context. You state the expected case. You mention the assumptions behind it, like simple uniform hashing. And you also acknowledge the worst-case scenario. This shows a deep, practical understanding of how these things work in the real world. So, let's wrap it all up. If you only remember a few things, make it these. First, Big O is about growth, not time in seconds. Second, be precise. Use theta for tight bounds and always specify the case. Third, don't forget space complexity, especially the call stack and recursion. And finally, be careful with multiple inputs. Keep those parameters unless you know for sure they're dependent. And I'll leave you with a little challenge. Go find a piece of code you wrote recently, maybe even yesterday. Now that you're armed with all this, can you analyze its true time and space complexity? What assumptions are you making? What's the worst case? Go find out.